Hey, my name is Chip, and today I want to talk about principles of good machine learning system design. A little bit about myself. I come from a very non-tech background. I started writing in high school, and I was working as a reporter, and then I was working on books, and I have published a few. And my first foray into technology was when I was working as a product manager, creative director for several products, including Coke browser, which is now the second most popular browsers in Vietnam with 20,000 million monthly active users. I also work on several other products which have been now acquired by VNG and Groupon. So when I went to college, I took my first computer science course because all my friends were taking CS. Then I found out they realized it. So I taught a course on TensorFlow at Stanford. And after graduations, I joined NVIDIA as a deep learning engineer, and I'm currently at Snorkel AI as a machine learning engineer and open source lead. So this is gonna be very quick intro about Snorkel. So Snorkel is an end-to-end, it's a platform, an end-to-end platform for developing AI applications. For more information, you can go to our website, but this is not a talk about Snorkel, so I'm gonna just skip it. For my talk today, I'm going to go over 5 points. So first is when to use machine learning. Second is machine learning in research versus machine learning in productions. And then the next is a few of the myths that I often hear from people who haven't deployed machine learning systems in productions. And the next is I want to introduce a framework, an iterative framework for developing machine learning systems. And the last is the 4 phases of machine learning adoption for business. So before we start any machine learning project, I think the first question we want to ask is that does it need machine learning or when to use machine learning? So to begin, let's take a step back and understand what machine learning is. So machine learning is an approach to learn complex patterns from existing data and use these patterns to make predictions on unseen data. And I have underlined a few of the words that we will go over. The first word I want to go over is patterns. Machine learning learn patterns from data. So for machine learning to be useful, there must be patterns in the data for it to learn. So imagine you have a fair die and you roll it to get the next number. It would be foolish to build a machine learning system to predict what the next outcome would be, because even though we know the distributions of the outcome, there's no patterns in how this outcomes come around. So previous outcomes would have no determinations on would have no effect on the outcome of the current roll. So the next is complex. The patterns should be complex. So if a pattern is simple, so imagine if you want to build an application to just map from a zip code to the state, then it's pretty straightforward because a zip code can be in only one state. So you can build a simple lookup table or several if else, and you will be able to do it. And you wouldn't need machine learning. So you would want, if you want to use machine learning, then you should learn some complex patterns. So for example, like if you give a pictures and it tries to predict whether there's a dog in it or not, is a complex patterns that machine learning can learn. And the next phrase is existing data. So it must be, you must either already have data, or it's possible to collect existing data. So you can look at, for example, like reinforcement learning. You don't need existing data right now, but you can, it's possible for you to like keep playing a video game to collect data as you play. So one applications that I think about is like it's fun to think about is whether it's possible to predict how much income tax somebody owes. Um, it's really impossible for me to do it because I would have no access to any information of people income or people the tax will already pay. But for a type of data that is inaccessible for one group of people might be accessible for another group of people. For example, like income tax data might be inaccessible to me, but it might be accessible for the IRS, and it might be possible for IRS to build these applications. But the question of like whether they should build it is another question. So the next phrase I want to go over is unseen data. After learning patterns from existing data, the model will make predictions on the data it has never seen before. For that to work, then the patterns must generalize from existing data to the unseen data. So consider a model to predict how many downloads an app would get on the App Store today. That model wouldn't work if all the data it has is from the App Store back in 2009. And the next is a fun one, predictions. So because machine learning models make predictions, it only work on predictive problems. So it can work for problems such as like, what would the outcome be like? So when people talk about predictions, they tend to talk about futures, like predicting what would be tomorrow, like the weather tomorrow, what would be the stock price in the futures. But here is us make machine learning really powerful, is that predictive problems are everywhere. So you can frame any problem as a predictive problem if you frame it as what would the answer to this question look like, or what would the solution to this problem work like. And so one category of non-predictive problems that have been that have applied machine learning very successful is the computationally intensive problems, such as graphic renderings. So in the past, if you want to show something on the screen, like you want to shade an object in the screen, you have to build very complex models and do like very intensive computations to get the shading right. But now with machine learning, you can approximate the shading, and you can predict what it would look like, and it has been extremely successful in a lot of animations or science fiction movie. So the next stage, we're gonna talk about machine learning research versus machine learning in productions and how they're different. So the first one is objective. So if you want to build any machine learning project, you probably have an objective in mind. So the difference is that like in research, people usually care about a single objective, which is often model performance. Like people try to build models that achieve something like the high accuracy, the highest F1, highest blue score. But whereas in productions, a machine learning project has many different stakeholders, and each of them might have very different objectives. I have a star nature model performance because it's actually, this discrepancy is something that people in academia have noticed and is being actively worked on. So if in the footnote, you can see the link to one paper that if you're interested in how the research community is trying to cope with it, you can check it out. So here's a few examples of like what stakeholders, what objective each stakeholder might have. So consider a big team, and there's like a smaller team, which is ML team. So the engineers might be very, very excited to build a machine learning model that achieve like the highest accuracy as possible. Oh, and also like they have puppies, because I actually have a collections of really cute puppies, and I try to like insert them in my talks because they warm my heart. So we have the machine learning teams that want the highest accuracy, and then we have product teams that might just want the fastest inference time. So they don't care like what model you using, as long as you can give as long as a request come in, you can output the result in like 1 millisecond or something like that. And then we have the salespeople. Like, for example, you're building a ranking system for the search engine. The sales group really just want a system that can help them sell the most ads. And then we have the manager. So the objective of the manager is to maximize profit. And in some cases, the quickest way to do it is just like to lay off the entire machine learning teams. And it might sound funny, but it's actually happens quite a lot. Like when a company is in a crisis, the machine learning team might be among the first to go. And the next difference is in computational priority. So in research, you want fast training with high throughput, and in production, we want fast inference and low latency. If you're worried about the technical terms, just give me a moment. I'll go over it. So just for a refresh, here's an example that I think is pretty useful in explaining the difference between latency and throughput. So consider this ant that's trying to move leaves from A to B. So if each time an ant can move only one leaf, then latency is the average time it takes for the ant to move a leaf from A to B, and throughput is how many leaves it can move in maybe 1 second, a minute, or like an hour. So if you're doing real-time predictions, as in you process one request as soon as it arrives and we process one request at a time, then reducing your latency also increases the throughput. Things get a bit more tricky when you do things in batch, as in you want to process multiple requests at the same time. So consider this the same ant. So now instead of carrying one leaf at a time, it carries two leaves. Then maybe it will take longer for the ant to get from point A to point B. But so it means that it has higher latency. But then it can actually over the same period of time it can carry more leaves. So now it has also higher throughput. In training, you want to optimize the compute power of the hardware or the cloud services. So you want to train, um, so you want very high throughput. But in inference, during inference, when you serve model to users don't want to wait, and you want to optimize for latencies. So during training, you might sacrifice latency to have higher throughput, but in inference, you might want to sacrifice throughput for lower latency. So the next difference is in data, and I think it's among the biggest points people talk about when they compare the research and productions. So in an academic environment, you work with very clean static data, and in research, data has to be static by nature, so that different teams, different research groups can benchmark their models and techniques on the same data. But whereas in productions, you work with data that is constantly shifting. So today the data looks so for example, if you work with text data, people might change the way they type. People might use new slang. So yes, they might change distributions, because like yesterday everyone's like last year everyone was talking about traveling, and this year everyone was talking about like quarantine, staying at home. So I think this is a pretty funny tweet from Andre Kapati from Tesla, and you guys probably have seen it because it has been shared a lot. I still find it funny. So the next point is fairness. So in research, it's very easy for researchers to think like, let's just focus on achieve state of the art first to show that the model is useful first before before getting to the complicated mess of fairness. But in productions, you can't really think that way. So in fairness, it's extremely important. Especially when we have systems that can make decisions at a very large scale. So when humans make predictions, like for example evaluating loan applications or a test score, we easily can do things like in a very a slow pace. So if humans are prejudiced, which are most people, if humans are prejudiced, then we can really make be prejudiced against a small number of people. But with machine learning models, if one model is biased, it can make sweeping judgment about many millions of people at a time, and this can be extremely sad. And the next point is interpretability. So most of us nowadays pretty like don't know how a microwave works. Like I don't know how a microwave works, but we are like comfortable with using it. But for machine learning, most people are still not okay with using machine learning without understand what it does. So here's a pretty popular tweet by Jeffrey Hinton. So he was asking about like if you have a AI surgeons who like with much higher cure rate, but like can't explain it, and a human surgeon's like with a less cure rate but can explain what he does, like which one would you like choose? And when I asked it these questions in a real life talk, I usually get the answers like 50 50, like 50% of people okay with AI surgeons and 50 people still want a human surgeon who can explain things to them. And here's a few of the myths about machine learning productions that I often hear from people who have never deployed machine learning models. So the first myth is that like deploying is hard. Everyone heard about deployment and they're scared. So the truth is that like deploying is not hard. Deploying actually easy. Like if you just want a model like for to show the friends or the family to play with, it's actually pretty straightforward. Like you can train a model, create an endpoint, and then like build a simple app like Streamlit. You can do it in like an hour or two. However, deploying it reliably is hard. Like if you want to deploy it so that it can serve like thousands of requests in a second, it's hard. If you deploy it so that it can if something goes wrong, you can quickly figure it out. It's hard. Keeping it up all the time is hard. So deploy models is only hard if you want to do it reliably and at scale. So the next one is that like it's like pretty cute. Like in research, you think about a model as a single model. Like yes, I'm working on this model to do this. And if you come from a research background, you might be tempted to think the same way in productions. But the truth is that like in productions, you can have many different models being served at the same time. So for example, if you have a if you run an app like ride sharing like Uber, you might have a model to predict the ETA. You might have another model to predict whether a transaction is fraud. You might have another model to predict how much the demand is gonna be, so that you can like give incentive to drivers to join or like calculate the search charge. So and you might have an application that runs in different cities or different countries, and you might need like different models for different part of the world like that. So bookings.com like has about like 150 models in productions. Uber has thousands, and here are some of the examples of models of the machine learning models that are being used at Netflix on different tasks. Another myth is that if nothing happens, model performance remains the same. So, I think this is just like you just think it's like if we just have some model out, you just leave it there and just let it work, and nothing's gonna happen. So the first thing is just like software. Have heard? I hope you guys have heard of the term software rot. If you haven't, it's okay. Like I already heard about it recently. So like as a concept of like software, if you leave this there, like something's gonna break and you need to update it constantly. So machine learning systems are a part of software. So if you leave them there, something's gonna break. And another thing about machine learning systems that make the quality goes down over time is called concept drift. So when you trained the model on existing data, as times go by, the current data shift from the data the model was trained on. So the longer time has passed, the more the new data has drifted, and the worse the model performance is going to be. So machine learning models are going to perform best right before productions. So if you want to get a sense of how much the model performance has decayed, one tip is that you can train the model on the data from data from 1 year ago, from 6 months ago, from a month ago, and to see like how the model performance degraded as the times in the past longer. The next fourth is that like you won't need to update the models as much. People will say like, okay, how often you update the model? Like once a year or like once 6 months. So I think it's like this one mind-boggling fact about DevOps that like I have so much respect for DevOps people to be able to put it off. So like even back in 2015, this is where the numbers was published. Like SC already developed like 50 times a day. Netflix like deployed thousands of times a day, and AWS like every 16 seconds. Then of course like you don't want to do at the scale for machine learning systems, but the point is that like you do want to like update the models as fast as you possibly can, because every moment that you wait, the worse the model already got. So when I talk about my about this to people in my friends in machine learning research, they say like, but like most companies don't deploy machine learning at scale. That like most machine learning engineers don't need to worry about this. So it's true. Like how many of the Google or Facebook of the world are there? Right? There's only one Google. There's only one Facebook. There's only one Amazon. So most company might have like might use like very small application to serve a very small number of users. So the first part about there are not many big companies in the world is true, but like the second part is not true, because even though there's a small number of very large corporations, they actually employed a very large number of employees. So here's a research from Stack Overflow. So it's basically about like 50% of software engineers work for a company with at least 100 employees. So when I did a similar questions on Twitter, I got a similar ratio for machine learning. So statistically speaking, an average machine learning engineer will probably work for a company that does machine learning at scale, and they should worry about this. And another so the last myth is I think it's mostly come from business leaders and not machine learning practitioner. So due to the hype generated, so yes, there's a I believe there's a hype on machine learning and AI recently generated by the media or by some certain people in machine learning with vested interest in machine learning adoptions. Um, some companies believe that if they use machine learning, they can transform the business magically overnight. And this high expectations has led to some disappointment, because when people start using machine learning, it doesn't generate as much return as they has hoped. So I want to say this like magically, like possible, but like overnight, no. So there have been a lot of companies have been just seeing like significant returns from machine learning. Like for Google, like Google has been able to use machine learning to improve their translation quality, to improve their search ranking, to sell more art. But like Google have also been like investing in machine learning for decades. And there's a graph that I think is pretty useful. It's just like the longer you have adopted machine learning, the higher the efficiency is gonna be. So if you look at this graph done by an algorithm very recently, so like for companies who have like have model in production for at least um at least 5 years, like 75% of them can get a model into productions like within 30 days. Whereas for companies, it's just getting started. Like 60% of them still take like more than 30 days at some point, like even like almost a year to deploy. So if you want to invest in AI, like try to like be patient, like spend time to improve the pipeline. Like I do believe that machine learning can help a lot with a lot of problems, but it's not gonna be like magical. So here's an iterative process for machine learning. Iterative process. So this is what I call a 10 out of 10 graph. Like the content is 9 out of 10 and the style is 1 out of 10. So I told the organizers that I want to use new materials for this talk. So this is like still work in progress. So like I'm trying to like draw out the iterative process for developing machine learning systems. And if you see like there's only one if you see like there's only one arrow from one step to the next, for the project scoping to data management to machine learning model development, and then deployment, maintaining, and monitoring and maintenance. See, I can't even read my handwriting. And then business analysis. The reality is that like there are a lot more arrows. Like you can have like for example, during business analysis, you find some insights might be useful to use for developing machine learning models, and you're gonna go back to the ML model development. And during monitoring, you realize there's something wrong and have to go back development again or go back to scoping. So this team are like extremely intertwined, and it can't really be easily being like it is not linear like that. So I think like so here, so in the most layer is a name of the stage, and the outer layers is what is usually known in the industry. So like project scoping, like it requires like product management or project management, and then like the next data management, like to collect, store, process, control, ingest data like with data engines. So you need it's like DataOps. And the next is like developing models, which include like creating training data, like labeling, feature engineering, selecting model, training model, distributed training, evaluating models, and is in machine engineering. And the next is like when you need to like deploy the model, serve the model, and keep a watch on like maintained and monitor models, then it's part of what is called MLOps. And the last is like you have the model output and how do you tie it back to the business objectives, and it's where data science come in. And after you get the insight, you might have the more information to scope the next machine learning project or improve the existing project. So and here like in the outermost circle layers is about like different skill sets that you need at each step. I think like there's only a few steps. Like it's always useful to like know in-depth machine knowledge, but I think like for some stages that in more machine learning specific knowledge is more important than others. For example, in machine learning engineering is extremely you need a lot of machine learning, or doing data ops and data science you need machine learning or some deployment. But like for maintaining, like a lot of it comes from DevOps, and for data management, a lot of it comes from system. So I'm gonna go over this very quickly, if you because we're now time, but you can see some of this on my course. I was just about to announce my course at the end of this talk. So because of this, I just want to like so I just want to emphasize this like machine learning engineering is actually a lot of it is not machine learning. So I feel like the world would be a much better place if like machine learning engineers learned existing software engineering tools instead of complaining about like, oh, we can't do this, we're gonna have the tool. So like if people know more about DevOps, I think like 90% of the machine learning production problems could go away. So yeah, so for people interested in this topic, I'm actually teaching a course at Stanford in January 2021. It's about machine learning system design. We cover all of what I've talked about in this talk, and I've been trying to make materials online. So if you have any questions, feel free to reach out to me either via Twitter or email. Thank you very much.